Respect. Respect. Okay, I need to do it because otherwise I don't know where to cut the setting stuff from the YouTube. Yeah, that's a coordinate system, but it's a respect too. So it's respect, and this is lecture number 3. We're still left behind the schedule. And even though I'm not going to speed up too much today, because what we're going to do today, we're going to discuss about the matters that are very, very, very important. And because they are so important, I need to go slowly to make sure that you understand all the details, because we're really building the foundations today, foundations that you need weeks to come. And that's why we need to take it slowly, even though that we are left behind the schedule. All right, so what happens today is that we can open the completely new story. And the completely new story is a constraint equations. How is that we can limit the motion possibilities between the bodies? We haven't discussed that yet, but today we're going to do it. Remember, all this discussion about motion, description of particles, is related to kinematics. The kinematics is a discussion where the forces are not accounted. No forces. Forces will come later, and if I look at that, so they will come next week if everything goes as planned. So next week, we discuss about forces. Today, if there's in-class quiz, and if there's an option which says something about the forces, it's incorrect. Why? Because we're speaking about the kinematics. Kinematics is a motion analysis without forces. All right? That's the one thing. So if you see in-class quizzes that there's something mentioned about the forces, it will be incorrect. What else will be incorrect? Correct. Rotation of particles. That's non-existing thing. That's a urban myth. That's a Santa Claus. So it's not in this class. So if there's option related to rotation of particles, it's always incorrect. Why? Because particles do not have rotational degrees of freedom. Remember that. Because this will be one of the options too. Don't vote that, please, because that's going to make me feel sad. Okay? So we'll look at the constraint equation. We're also going to take a look at something that is called number of degrees of freedom. This means what are the different ways that the mechanism, multi-body system if you may, can move. How many different ways it can move. That's what the number of degrees of freedom is standing for us. And it will be counted based on the number of generalized coordinates and the number of constraint equations, which you do not know yet, but you do know the concept of generalized coordinates. All right. But prior to constraint equation, let's summarize what is that we learned a week ago. So a week ago, we learned that our mission here is to describe particles with respect to reference coordinate system. The reference coordinate system, which you can call it as a global coordinate system or whatever you want, is a coordinate system that typically standing still. It can be moving as well, but we're speaking about the reference coordinate system. In this picture, the reference coordinate system is this one here. Oh, this one here. So our mission is to describe every single particle with respect to that coordinate system. How are we going to make it happen? We can use the fact that particles cannot move relatively with respect to each other. Why? Because we're dealing with the rigid bodies. If we would deal about the deformable bodies, that assumption is not valid. But here it is valid because we're looking at the rigid bodies, which is a assumption you do not see in real life. Every single body is a deformable body end of the day, but we are assuming that deformation is not making influence to its dynamics. That's our assumption we do. All right. So how are we going to make this happen then? So we're going to use something that is called body reference coordinate system. Body reference coordinate system is this one. It is attached to body. So body moves, coordinate system follows, the body rotates, same story. Now, we're going to use the kinematics in such a way, the kinematic notations that we can first describe Where is origin of the body reference coordinate system with respect to reference coordinate system? Using vector R. Vector R consists of two components, projections along this axis and this axis. And then we're going to use 2 by 2 rotation matrix to take the rotation of this coordinate system into account. All right, that's the mapping. Mapping that converts description from one coordinate system to another. And then this is gonna be defined as a matrix A. And then we're using vector U bar to define one single point, particle if you may. All right, and so if I say the particle is located here, my vector U bar goes here. It's a little bit of a messy picture. So this is where the particle is located with respect to reference coordinate system. That's called R. That's our kinematics. That's what you have to follow no matter what. Every now and then in life and multi-body system dynamics, there are temptations. There are temptations to make a life easier. And here the temptation could be that in some occasion it look that there is a shortcut to particle. Never ever take a shortcut. Always travel via body reference coordinate system. That's how it goes. All right. So here is the kinematics I just mentioned. So I have here two components, one that is taking care of the translation and the one that is taking care of the rotation. Right. This one here is a 2 by 2 rotation matrix that is mathematically orthogonal, meaning that if you make vectors out of these columns, these vectors will be perpendicular with respect to each other. Perpendicular in planar case means that they will have 90 degrees angle with respect to each other. Okay? They are also unit in a length, as is the case of coordinate axis, x and y. They are unit in a length. And then this one here is this vector u bar we discussed a little while ago. That's a kinematics. Always, always, always follow this kinematics. And now it's confusing because we're using this vector u bar vector to define where the particle is located. So the particle do not have a rotational degrees of freedom, but body reference coordinate system does. Don't get confused about that. You understand the difference between the point and the body. Point, no rotational degrees of freedom. Body, yes, rotational degrees of freedom. I see that team blue, was it team blue? What is your team name? Blue? Are you saying yes? What was another team that I met a week ago? Was it Team Belgium? Is it Team Belgium here today? No? No. Team Finland. Is that Team Finland here? No. Yes, it is here. So is it what the Team Finland is saying? Yes. What about the Team Adults, which is online participants? What is that they say? They say rotations. A little bit of delay. How serious it is? Okay, 10 to 15 seconds is not bad. But I can tune it. I can make it shorter than that, but that comes with the risk that the streaming is not healthy anymore. So let's not do it, because I can see that the excellent connection. Okay, so with that, what about in three-dimensional space? How is it we can describe particle in a three-dimensional space? Same concept, different dimensions. Different dimensions in the sense that this vector R will consist of three components because of the three axes. Rotation matrix A will have a dimension 3 by 3. And the vector U bar consists of three components. Again, because of the three axes. Okay, this guy here, this rotation matrix, one way to describe it is based on Euler angles. Euler angles is a method that is using three successive rotations. Successive means rotation after a rotation. So how it happens? It happens in a way that you have two coordinate systems initially parallel with respect to each other. And then you introduce in the rotation, which is amount of phi. Well, so Mustafa is not listening to me, but this one here, the phi, okay, amount of phi around the z-axis. Then you have coordinate system once rotated, and then you introduce in the second rotation, this time around x-axis, amount of theta. And again, you have 2 times rotated coordinate system. This time you introduce in the rotation psi. I knew it. I just wanted to test it if you guys know. So psi. Okay, so, all right. So what do you do then, mathematically, is that you're describing each one of these rotations like shown here. And the successive rotations you can take into account by multiplying these matrices together. And this is how it looks. Don't bother to memorize it. Makes no sense. You do not need that. But you need to understand the concept itself. Okay. All right, here's an example. So there is a question which says that the body rotates 90 degrees around x-axis, because you see that this v here is obviously x-axis. Define the rotation matrix by using Euler angles. And this is a matter of substitution. So the first angle is going to be 0. Second angle is the one that I'm asking here, 90 degrees, which is a p divided by 2. And the third angle is 0. Once you do the substitution, this is how it looks. No thinking, so just substitution, and that will do the job for you. Okay. Tips for weekly assignments. Be careful with the radians and degrees when you're using trigonometric functions, because they will make a significant difference for sure. So make sure that you're not getting mixed about degrees and radians. If you need help, you can email me, but I'm going to forward your message to Suraj, because he is the one that is responsible of weekly assignments. I can try to help, but some of the assignments are so difficult that I'm having a hard time by myself. So that's why I need to use the help of Suraj. So you can email to me too, but don't expect, and by the way, I tried to keep it response delay within 24 hours, but I was unable to do it that last week because so many emails. And also the Saturday is something that I don't check my emails. So Saturday is exception here. Any other day, I try to do it 24 hours. Okay? You can complain too if you're not getting the response within the 24 hours, but that need to be related to this course content. Then I promise that. Okay? All right, then still one more thing about the summary. This is how you can define the velocity. Very mechanical. And once we set the kinematics, it's very important to be consistent, all the time consistent. And you're going to learn this consistently along the course of, when we're looking at the different things in this course. Okay, so we differentiate particle position with respect to time. We've got two components that are translational velocity and angular velocity. When you differentiate this one more time with respect to time, we got acceleration. Acceleration consists of three components. Translational acceleration, normal acceleration due to the rotation, angular velocity. So acceleration is quadratically related to velocities, okay? And then tangential acceleration due to the angular acceleration. That's it. Three acceleration components, meaning that later when we relate our inertia will have three different kind of components, or two different kind of components. One that is linearly related to acceleration, and the one that is quadratically related to velocities. Correct. You heard me correct. So there will be inertia component that is quadratically related to velocities. And you are really, yes, but you're going to learn that a bit later. So no worries today, but that comes a bit later. Okay, constraint equation. Finally, constraint equations. This is where we are at. And there's a lot of details to look at. But this is, roughly speaking, motion limitation. The way we can connect bodies together. How we can do that mathematically. We know how to do that in a real life. There are different kind of joints, revolute joints, translational joints, so on and so forth. But how we do that mathematically, that you're going to learn today. Okay. Now, as mentioned here, what these constraints is doing for us, it is limiting the motion possibilities, and it's making the mechanism to behave the way we want it to behave. An example is this crankshaft mechanism. So if I take a hold of this piston body here, and I move the piston body to the left-hand side, neighboring bodies that are connection rod and a crank will follow the certain way. Why? Because of the revolute joint that is here, here, and here. They will limit the motion possibilities. And this next, we're going to take a look how is that we can describe these motion limitations or motion limiters, if you may. That's the one way to say it. Okay? So it goes like this. Let's first look at the big concept, and then let's look at the details right after that. Okay, remember what we learned a week ago. So we learned a week ago that everybody needs 3 generalized coordinates. Always 3 generalized coordinates. And those 3 generalized coordinates are Rx, Ry, and theta for everybody. Now, if I have 3 bodies, how many generalized coordinates I need? 9, correct, 9. Because 3 bodies, 3 multiplies by 3, that's 9. So if I have 10 bodies, I need 30, correct. That's how it goes. So that's the amount of coordinates I need to describe every single particle, not particle, bodies in my system. Bodies in my system, okay? All right, then you can make a vector or kind of you can list these variables. You can put this in a vector which is called generalized coordinates. Number of particles and what they are depends on how many bodies you're dealing with, all right? So if I have just one body, this vector consists of 3 components. 2 bodies, 6 components, so on and so forth. Makes sense? Okay. But then I'm going to introduce another vector. This time is very unclear. It's just a concept for you. And this another vector is this constraint equation, these motion limitations. Motion limitations that connects these coordinates together. So these motion limitations are a function of generalized coordinates and possibly time. And there is a certain number of these motion limitation equations. Let's, when you look at it here, there's 1, 2, all the way to NC number of motion limitations. Now the number of generalized coordinates versus the number of motion limitations will tell you the number of degrees of freedom. But we need to take a look at the details, like how exactly you can do this motion limitation. And we do that in several different cases. So that's what follows. Here's the first example. First motion limitation that connects 2 bodies. So I have 2 potato-shaped bodies. And in these 2 potato-shaped bodies, there is a revolute joint that connects these bodies together. All right? So this revolute joint is located here, point O. How we can introduce this kind of revolute joint that limits the motion possibilities in such the way that these 2 bodies, they can move like this, together like this. They can move together like this. They can move together like this. And they can move relatively like this. But they are no longer move like this. That's no longer allowed because the revolute joint is not allowing them to do so. How we can make it happen? We will use kinematics we learned a week ago. So we're going to define this point O using equation that we are very much familiar with, using body A. Well, let me call what these bodies are called. Oh, they're called A and B. So I'm going to define this point here, which is you can call it particle again, using this body A. So I'm going to travel here. I'm going to take body orientation into account by using this rotation matrix. And I will use a vector U bar to go this location. That's going to be my first part of the constraint equation. Second part will be doing exactly the same story, but using body B. So I'm going to put this equal, then the same equation, but body B. This is A. Oh, sorry about my handwriting. A and B. You set them to be equal. That means that this point have to be equal to both of the bodies. So that's a motion limitation, mathematically expressed. Okay? Let's make it happen. So here's a concept, what I just mentioned. Point O using body A equal the point O using body B. All right? So let's look at the details. Very mechanical. No thinking. Absolutely no thinking here. Just do it mechanically. Okay? So here's a component of this guy, this translation guy. These are the rotation. This is a vector U bar. And the same for this guy. Goes here. You take the orientation into account, the vector U bar. You put everything to left side of the equation. That's your constraint equation. I have now here two constraints. Yes, sir. Okay, so the question is such that now if there is a potato-shaped body here, like A, and a potato-shaped body here, B, how you connect these together? Well, if you want to connect them together using revolute join, how you do that in a real life? By putting them to be together, because otherwise you cannot. So this, even though that this is mathematics, is not so far away from real life. Because think about that, you have this guy and this guy. You wanted to introduce the revolute joint. How you can do it? You have to make them merge in this joint location. If they are like this, there is no revolute joint like this big. It's not going to happen. There are different kind of joints that they don't necessarily need the body to be so near to each other. But this revolute joint is the case where they need to be close to each other. Okay? Is there Team Belgium today? No? Last week, the week ago, there was a Team Belgium for sure. But now I guess that there is, but you guys just fail not to be my friend. That's okay, I'm used to that. I'm not even disappointed. Okay, all right, but two constraint equations. All right? Remember what I just discussed. I said that this revolute joint allows these bodies to move this way, this way, this way, and relatively with respect to each other. That's a total of 4 different ways. All right? How many generalized coordinates I have when I'm dealing with the two bodies? 6. Okay? 6 minus number of constraint equations is going to be my number of degrees of freedom. 6 minus 2, 4 degrees of freedom. So this is a 4 degrees of freedom system. Somebody was voting in the chat too. Correct voting. So here's the number of degrees of freedom. Here's the formula to compute the number of degrees of freedom. So ingredients, components needed to compute the number of degrees of freedom are number of generalized coordinates. How we know that? We know that when we know the number of bodies. 10 bodies, 30 generalized coordinates. 2 bodies, 6 generalized coordinates. How many constraint equations we need? Well, that depends what kind of joints we will introduce. Some of the joints in planar case, they need 2 constraint equations. Some of them need just 1. Okay, but that's going to be the number of degrees of freedom. That's how it goes. Now, the number of degrees of freedom can have 3 different scenarios. And now I recommend that you take everything aside. Put everything aside. Look at me, because I have some important information that I would like to share with you. Now, breathe very deeply. And one more time. Now, these different scenarios are such that if the number of degrees of freedom is more than 0, 1, 2, 3, and so forth, we have a system that is dynamical system. Dynamically driven system. What that means? It means that, for example, this crankshaft mechanism will have a 1 degree of freedom. And this 1 degree of freedom is actuated by force. Where is a force? Force or a moment. Moment, which is introduced to this body, this crank body, is my force. This is dynamically driven system. And to solve the response of dynamically driven system, the only way to make it happen is that you have to create equation of motion, and you have to solve the equation of motion in forward of time. That's the first scenario. Second scenario is that the number of degrees of freedom is equal to 0. Where you can find a case like this? Well, you cannot find them in a real life, but you can find them in mathematics. And they are like this crankshaft mechanism again, same story, but this time I'm introducing motion. I'm introducing the motion, not force. Motion is a constraint, as is a revolute joint. Different type, but it's a constraint. The 1 degree of freedom goes to 0 degrees of freedom. That means that I can solve the response by using kinematics, using constraint equations only. Nothing but the constraint equations. And that's the solution that tells me how the system moves in forward of time. Okay? If we have a time today, you can learn how to do this kinematic analysis, motion analysis, when the number of degrees of freedom is 0. Number of degrees of freedom is 0. Number of degrees of freedom is 0. This indicates that there may be, or maybe already open in-class quiz, which is related to this subject matter. I'm not telling, but I'm implying. I'm implying. Or it could be the case that number of degrees of freedom is less than 0. System is unable to move. It simply cannot move. So here are the cases. This is where the system where the number of degrees of freedom is less than 0. This cannot move because, the 1 degree of freedom, there is 1 extra revolute joint that takes this connection rod to ground. No motion. This is kinematically driven, dynamically driven. Now, if you have any doubts, what is what? What is a kinematic? What is dynamic? This will be a good time to raise a hand and say, hey, Aki, I don't understand. Can you be more clear? And remember what that comes along? Correct. But because you have such a big brains, you have no difficulties whatsoever, so you understand this immediately. Right. You figure this out already when you step into this lecture room, maybe even earlier than that. Okay? So no problems. Team guys back there, everything is okay. Very good. Okay. Number of degrees of freedom in kinematically driven system is what? No, I'm not going to mention that anymore. But And the game is on. So what is the success rate today? No, it will not. No, it will. It will not. But how high it goes? 90. So Mustafa, he had a good sense of what what the how high the success rate can be. He's saying 90, 96. And look at me, my hands is visible all the time, so it's not me that is voting incorrectly. So it's you, one of you. Okay, so we get back to that. Ah, there's somebody saying that there's going to be a dance today. I don't think so. That never happened because I don't know how to dance, so I can make a promises like that because I'm in a safe side. All right, so let's continue then. Here are the number of constraint equations needed. And I mentioned earlier that this is ranging from 2 to 1. I was incorrect, so it's ranging from 3 to 1. So if there's a fixed joint, then it's 3, which, by the way, is not a good idea to model. Not a good idea. You will learn that later, why it is not a good idea. But simply stated, because everybody needs 3 generalized coordinates. Everybody needs 3 generalized coordinates. And that's the case also the bodies that are connected to ground. So we'll have 3 generalized coordinates, 3 constraint equations. Depending on the method we use, these are typically summed up. So they are summed, meaning that's going to be 6 unknowns for nothing, because you know that the body that is fixed to ground will not move. So there's nothing to solve. All right. Revolute joint, we learned that already earlier today. That's going to be 2 constraint equations. Okay. Translational joint, that's going to be the same story. Primitive joint, regardless how you do it, we'll just take one, or we'll need 1 constraint equations. Okay, let's practice. Let's practice a little bit. So here are the 2 different kind of mechanisms. So we're going to practice a little bit, and then there's going to be another in-class quiz, but I'm expecting you to do the math. Fair enough. All right. What is the number of degrees of freedom in this case? So let's first count the number of generalized coordinates. How many moving bodies I have here? So let's count this. I have here 1, 2, 3. How many generalized coordinates? How much? Not 9. Correct. That's 9. 9. All right. Then let's count how many translational joints I have. 1. 1 translational joint. So that's minus 2 plus. And then let's count how many revolute joints I have. I have here 1, 2, 3, 4. 4. Happy? Are you happy? You shouldn't, because this is not joint. This is just make you feel confused. All right, so this comes 2 multiplied by what? 3. Sorry about unclear writing. So that's going to be 6. That's going to be 2. So it's going to be 8 constraint equation, 1 degrees of freedom. 1 degrees of freedom. All right? So you got it. All right, we'll do it. I'm too scared to take my drawings away because if I do it, then this overhead projection is not willing to cooperate with me anymore, and then I need to do all these settings again. All right, so let's go this slowly. How many bodies I have? How many moving bodies I have? This is my first moving body. This is my second moving body, and the box is my third moving body. 3. 3 multiplied by 3 is 9. Okay, so it's 9 generalized coordinates. I have 1 translational joint here in the middle. Okay, so that's going to be minus 2 plus. Then how many revolute joints I have? 1, 2, and 3. So it's going to be 2 multiplied by 3, because 3 revolute joints. That's 8. 1 degrees of freedom. You all agree? Are you sure? Are you absolutely sure? Because you should. Remember, can-do attitude, high self-confidence, Elvis kind of attitude. Okay, so it's 1 degrees of freedom. Okay, the next. How many moving bodies? This is a little bit unclear drawing, but these are hydraulic cylinders. Hydraulic cylinder consists of 2 components, which is a cylinder and a piston. Okay, and these 2 bodies are connected together via revolute joint. So how many moving bodies I have here? Okay, let me repeat. So hydraulic cylinder consists of 2 bodies, cylinder and a piston. This is a 1 hydraulic cylinder. Both consist of 2 bodies. So how many bodies I have in total? 4, correct. Meaning how many generalized coordinates I have? 12, correct, 12. All right, then how many translational joints I have? 2, because 1, 2. Okay, so it's going to be here 2 multiplied by 2. Where the 2 is coming from, because translational joint needs 2 constraint equations. How many revolute joints I have? 1, 2, 3. So that's going to be 2 multiplied by 3. That's 4. That's 6. 2 degrees of freedom. 2 degrees of freedom, because if the both cylinders get longer, it moves downwards. If one is getting longer, one is getting shorter, it moves like, yeah, sideways. You're with me? Why are you so quiet today? That is because it's a Monday, right? Yeah, sorry about that. But people in the student affairs office, they don't like me. So they either keep me Monday morning lectures or Monday afternoon lectures. And I figure that Monday afternoon is better than Monday morning. All right, so number of degrees of freedom. Okay, let's take a look at the in-class quiz. First one. Hold on, so I need to take a look at this one. Okay, you guys don't see this. Okay, so I would like to share this with you. So just a second. Yep, here it is. Okay, so what's the success rate? So what are the cases? 96. 19. 99. Okay. Is it going to be 100? Is it going to be 100? Yes or no? No. Okay. Ooh. Ooh. Close case. Very close case. But not 100%. Okay, so I felt a bit nervous, to be honest, because I was repeating that zero so many times that I thought that this is going to be dangerous to me. It wasn't. So I guess that I can be more relaxed next time, so I can tell you even more. Okay, so the success rate is, we were pretty close. 95. 95. 95. Okay, let me take us back to. Last example. Okay, so let's go to this. Okay, this in class quiz, I'm gonna put it on, but you can wait a while because this goes to next. This one. Take your time because I'm gonna explain. Oh, you see this well. I will explain this example. Uh, this example one more time. What happened now? No, this is in a different mode because it's not allowing me to draw. I guess so. Ah, and go and discuss with your fellow students. Remember, I'm here ready to discuss with you too. Okay, this example. All right. Oh, sorry. All right. So in this second example, I have two hydraulic cylinders. Hydraulic cylinders, when you look at the cross section of them, they look like this. There is a cylinder and a piston. Now this is a one body, this piston, and the cylinder is a second body. All right, this piston moves like a translational joint with respect to cylinder. That means that these two, one hydraulic cylinder has two bodies. Okay, these bodies are connected together via translational joint. Okay, now this is my first hydraulic cylinder. This is my second hydraulic cylinder. That means that there is a total of four moving bodies. 4 multiplied by 3 is 12. 12 generalized coordinates. Then I'm going to take a look at the constraints. I have here 1 and 2 translational joints. Each of them needs 2 constraint equations. Then I'm taking revolute joints into account. So there's 1, 2, and 3. So it's going to be 2 multiplied by 3. That's going to be 6, 4, 2 degrees of freedom. Okay, back to this. 100% or not? No, not 100%. But how much if not 100%? 45. Yeah, by the way, I see that there is quite a bit of delay because I'm coming back right now, like 15 seconds or so. Okay, is there a bowl on the right side? Okay, hold on. So this description is unclear. So what I have here, I have two bodies, two moving bodies. Okay, then I have revolute joints, and the primitive joint, which means that this point here has to be in this slot. It can go up and down, it can rotate, but it cannot move this direction. It cannot move left and right, correct. So that's my primitive joint. Okay, but what is the number of degrees of freedom? How you can do the math? You count how many moving bodies you have, all right? Then you know that everybody needs, in addition to love, they need 3 generalized coordinates, correct, in planar case. Okay, then you count how many revolute joints you have. Each one of them needs 2 constraint equations. How many primitive joints you have, each one of them needs 1 constraint equations. That's your math. Okay, so I will leave you to think about that, and I see that is about time to have a break. Would you like to have a break? No? Okay, so let's continue a little while, and then you can have a break. Okay? All right. A little bit of wordings, a little about terms, which is not so significant, but for your information. So, what the different constraints are called with. So, holonomic constraints are the ones we're typically looking at. Those are the ones that are function of generalized coordinates. They are like revolute joint, translational joint, so on and so forth. Then there's a non-holonomic constraints which we will not touch in this course. Non-holonomic constraint is like when there's a rolling in surface, disk rolling in a surface. That you can describe by using non-holonomic constraints. We are not going to take a look at those, so you can be safe. Then there's a scalenomic constraint, which are time dependent. So they are kind of like driven constraint. There's a constraint that says, okay, this pen have to move this way along the time. That's driven constraint. So you're like driven, introducing the motion to the system. All right? That there is a rheonomic constraint, which or time dependent. I'm sorry, I said incorrectly. Scalenomic is not the one that I wanted to say. Rheonomic is the one that is driven constraint. Sorry about that. Okay, so those are the different names. This is for your information. Okay, in a three-dimensional space, how it goes then? Well, you need more constraint equations. And this table shows, what if you have this type of the joints, how many constraint equations you need. Just to give you an example, if you have a revolute joint, you need to use 3 constraints to limit the translational motion and 2 to limit the rotational motion. A total of 5. Okay. Same for translational joint, but the different thing. So it's going to be 3 rotational degrees of freedom, 2 translational degrees of freedom. And then different combination of, depending what kind of joints you're dealing with. You can also use something that is called joint primitives, which allow you to combine different pieces of joints together. So then you can make any kind of model and any kind of motion you want, as you can see from this table here. Okay, one more information is redundant constraint. I have here a door. You know the mechanism. I'm sure you have used it before. Door. So you can put it up, and you can close it or keep it open. Okay, so how is that the door? Let's count the number of degrees of freedom in a door. Okay, so now we are in a spatial case. In a spatial case, we have 6 generalized coordinates for each body. Okay, so this door needs 6 generalized coordinates. Translational joint needs how many constraint equations? 5, because of this table. Here is a 5, total of 5. So that's going to be 6 minus 5, so it's a 1 degree of freedom. That seems to make sense. But how is in a real life, when you look at the door, they're not constructed by using 1 revolute joint, but 2 or even, sometimes even more than that. So let's count at how many degrees of freedom we have in real life, real doors. How many generalized coordinates? 6, because no difference between this case and this case. And then I have here, that's supposed to be minus, of course. Minus, and then how many revolute joints I have here? 2. 2 multiplied by 5, that's 10. Minus 4. Minus 4. Minus means that system is unconstrained, over-constrained, meaning that it cannot move. So this is it. End of the story. So we are locked in this lecture room the rest of our life because it was just mathematically proved that it will not move. Scary. What explains this? Are you happy? You agree with me that we are not allowed to go, we cannot go outside of this lecture room? What do you think? Can we, let's vote. Can we go out or can we not? Who is voting we can? We can. We cannot, because mathematically proves we cannot. But in real life, what do you think? Can we go or can we not? We can. So how come? Because mathematically all became clear. So it's -4, meaning over-constrained, meaning not moving. What explains this? Okay, so the result, what was this? You said what? There's a two constraint in one axis. That means mathematically that these constraints are not independent. They are not independent with respect to each other, so they're constraining the same degrees of freedom. That looked at this, there is too many constraints. But in reality, there's not, because they eliminate the same motion possibilities. This kind of system is called redundant constraint, redundant system. There's too many constraints for one motion possibility. You can end up to have this kind of problem when you to put two revolute joints here. That would mean that there is a kind of like over-constrained system. But these constraints are not independent. I don't know if you guys look at the lecture notes. Did you? Now would be a good time to make an impression to me and say, yeah, of course. I have it in my, next to my bed. So I read it every day. Because there's no way me to go and check. So in lecture notes, it says this, independent constraints. So this single word makes a big difference. So it's all about independent constraints. Four-bar mechanism. Let's count it in a three-dimensional space. What is the number of degrees of freedom? Moving bodies is 1, 2, 3. 3 multiplied by 6, 18. How many revolute joints? 1, 2, 3, 4. 4 multiplied by 5, that's going to be 20 minus 2. Redundant. So it's a redundant system. Some of the commercial software, if not all, I think all, they can recognize that there are redundant constraints. They will eliminate those redundant constraints from your model, but you need to be careful because the way they will be removed will affect your reaction forces. So you just need to be careful with that. And a good modeling policy is not to use redundant constraints. So you can, instead of using revolute joint here, you can use inline constraint as an example. Okay, there are more examples are about to come, but I can tell you from your face that you need a break. Okay, is it going to be 100% success rate regarding that? No, but how low we go? How much? 7. So the first digit will be 7. What is going to be the first digit? Oh, somebody's saying 5%. That's low. That's very, very low. 5 is too low, I think. I hope. Okay, so let me. Would you like to see the results? I mean, the audience? Oh, you don't see it at the moment. So, okay, so we will take a look at the P duplicate. Okay. All right, so what is the correct number? One and two. One and two. No, it's a one, need to be one. Just tell me one number. Correct. 84. Very good. But not 100. Okay. So let me take one more thing. And I know you desperately need that break, and I will give it to you. But one more story. And this story goes like this. Ah, I need the first. Okay, you see it now. Okay, let me take ourselves back to this one. All right. How many moving bodies? Two, three. This is not moving because it's connected to ground via fixed joint. So how many moving bodies? Two. How many generalized coordinates? Seven. Six. Six. Mustafa, you cannot help here. So this is unfair because you already have that many against me, and I'm alone. Okay, so then how many revolute joints? Two. How many privative joints? None. One. How many is that? This is five, so it's one. All right, so there's going to be mechanism like this, like this. Hear me, like this, which I will ask again. What's the number of degrees of freedom? Can you do the math? Yes, it's like can do. Yes, I can. Okay, so when is that you would like to be back? And the answer is never, but because you need to be back. So what time you would like to be back? How much time you need to relax, to recover? 10 minutes. 10 minutes. Okay, 10 minutes. So that's going to be 5:25. 5:25, we will be back. I will keep the streaming on. So 5:25, please be back. Should we try to get rid of this delay? No, no, it's too risky. It's too risky business. Yep. Okay, it's 5:25. Time to get started again. I see that some of the participants in the lecture room they disappeared. I don't blame them. Maybe I would do the same. They did not came back, but they left their gears here so we can keep them. Yeah, okay, very good. So during the break there was a request that can I explain where this number six came in some of the examples, and some of the examples that came are this one. Okay, so now I know that this is a bit confusing. That I mentioned in the beginning that this course is mainly focused on two-dimensional cases, cases where we're looking things in a two-dimensional space. But there are a few exceptions. That the one is related to these rotations, and here is another exception. These particular joints are in three-dimensional space, in spatial case. Spatial case. In a spatial case, one body needs how many generalized coordinates? 6. Planar case, it needs 3. All right? So now, there was a question like where this number 6 came in this door case. And that came from the fact that the door is described in three-dimensional space, meaning that it consists of 3 generalized coordinates. So a different story then. And here too, this too is a three-dimensional system. And now that's all about the three-dimensional system. We're going to focus on two-dimensional cases from this on. Okay? Okay, let's take a look at the example then. So I have here very simple mechanism that consists of one body only. And the one body is connected to ground by using two primitive joints. Here, point P is connected to ground in such the way that this P has to be along this line all the time. It cannot move in a global y direction, but it can slide along the global x direction, but not this direction. This motion is not possible. Then I have another primitive joint, which is located at another end of the beam-like body. And this one is opposite than the one we just looked at. So this one can slide up and down, but it cannot move left and right. Okay, so these are my joints. What is the number of degrees of freedom? Okay, what is the number of generalized coordinates? No, you cannot tell. By the way, my voice is on. What is the number of, okay, maybe we shouldn't have breaks anymore because you go, I don't know where, and when you come back, you have absolutely no idea. Like, what course is this? You're completely off. So maybe we should just lock the door, stay here until everything becomes to be clear. Okay, what is the number of generalized coordinates? 8. 3. Okay, that's correct. 3. Because of what? How many moving bodies? 1. 1. Okay, it's not difficult. All right, then how many primitive joints I have? 2. How many constraint equations each one of the primitive joint needs? 1. So the number of degrees of freedom is 1. Correct. So it means that this kind of is like, okay, this is going to be a challenge to describe how it moves. You can imagine that in your head. So you understand it goes like this, kind of. But it's a little difficult to describe. Okay, I don't even try to do it anymore. But anyway, so you got the concept. Okay, and we need to define constraints, constraint equation. Define constraint equations. Okay, any idea how we can do that? Can we simply use this equation, the only equation we know, because so far we learned one equation, so can we use it? We have to because we have no other choices. We know no other equations than this one. This is the only equation we know. So let's use it. So let's get started here from the reference coordinate system. Let's first travel to origin of the body reference coordinate system using this vector r. And then we're going to go left and right, depending which one of these two constraints we would like to introduce. So that's it. That's how it goes. So let's get started from O, this one. So first we're going here to here. Is this vector r. Okay? Then we're going to take the orientation of the body into account. It's going to be this one here, 2 by 2 rotation matrix. And vector u bar. What is a vector u bar? Look, we here. We're pointing this direction. So how much we need to travel along the x direction? Local x direction. L divided by 2. Because it's a positive direction. How much y direction? 0. Okay. Then comes constraints. So this is where the joint is located at. And that position is amount of d from the origin of the reference coordinate system. So I have to set x direction to be equal to d, which is a number of some kind. So this d here is going to be my constraint. This can be as it wants. No constraint introduced here. So once I do the math, once I take this component here, I multiply this by this vector. I'm going to set that to be equal to d, and I move d to be in the left-hand side of the equation. That's going to be my constraints. Are you with me? Makes sense? Okay, what if this would be, this point would be d plus c? Then this would be d plus c. Okay? Makes sense. Next one. How is that we can describe this constraint? Same concept, over and over and over again. So we're going to use this equation. First, we're going to go here, and then with help of vector u bar, we're going to go here. And then we're going to set the constraint. Very simple. Okay, here's the first translation. This is my 2 by 2 rotation matrix. Now, look at the positive x is pointing this direction. So I need to move minus L divided by 2, minus. How much in a y direction? 0. And I'm going to set my constraint to y direction. Y direction. That's going to be my second constraint equation. Very easy. Not difficult. Good. What is that the constraint equations are doing for you? Okay, so let's look at them together. So remember remember. Okay, let me take us ourselves back to this slide here. Where is it now? This one. So the constraint equations are embossed to generalize coordinates. So that's they kind of like action and the reason we wanted to introduce them. That's what they do. Okay, so that is mentioned in a different way in one of these choices. And the choices are interconnect generalized coordinates. Interconnect, meaning that they combines, they're creating relations between the generalized coordinates. They define center of the mass of the body. they define physical dimension of their body, define a particle rotation. One is very much off, one is correct. Okay, no, this is not yet on, so let me put this on. Here, constraint equations. What is a function? Oh, yeah, I'm not going to show that because this annoying system takes it too slowly. We get back to this momentarily, all right? You say nothing yet. Yep, here it goes. Okay, would you like to get some help? Or is it this is clear? This clear? Everyone clear? Okay, for online participants, here the people in the lecture room, they say, okay, can do attitude. I know exactly what is the right answer. No problem whatsoever. And I see that, okay, so there are comments which I'm not willing to mention to you because they are related to this final option D. Okay, now here comes something that I will be a little bit brief because there's one very exciting in-class quiz left, two actually, but one that is very exciting that I still would like to do today. So this is how is, the next example is how is that you can do the translational joint. Okay, this is a mathematical, a little bit involving. So this is not as easy as this translational joint, but doable. So I have here two bodies, A, which is a beam-like body, and a beam, which is a box-like body. And these two bodies are connected together in a way that body B can slide along beam-like body A. Okay. And now I would like to introduce the translational joint within these two bodies. How can I do that? So I need two constraint equations. One will be very simple. Hey, Mustafa, I got the warning. I guess it is not serious. So it's just complaining that I'm not smooth anymore. But I think that's because of the subject matter, not because of me. Yeah, I see that in my YouTube studio. It seems to be okay. No comments, no complaints. But I see that there is an error in the screen. Anyway, so two constraint equations. One is very, very simple because what this translational joint is doing for you, it is saying that the relative rotation between these two bodies is no longer possible because they're sliding along. They cannot move like this. So that's constraint. And that's very simple constraint. So I'm going to take the rotation of the body A, rotation of the body B, and set them to be constant. N could be 0 if they are oriented as it is shown here. C in the scenario shown in the picture is equal to 0. All right? That's going to be, yeah, it seems that everything is okay. So that's going to be my first constraint equation. Second constraint equation is a big pain because I'm going to introduce two vectors and I'm going to use a perpendicular condition of these two vectors to set the constraint that allows them to slide along. All right? So that's going to happen in a way that I'm going to introduce the vector k, a vector h. H and k will be perpendicular with respect to each other. And k will be the one that connects bodies A and B. This h will be related to body B only, and that's going to be kind of what I need to define this sliding along condition. So here's a magnification of the situation. going to be pretty fast today. I'm not going to look at that very much in the details, but if you need details, take a look at the lecture notes. All right? So I'm setting 3 points, O, P, and Q. And now I'm going to repeat this whole story again. So I'm going to define point O, point P, point Q using the only equation that I know. And what is that equation that I know? Well, that is an equation that defines the kinematics. This one. And then using these 3 points, I can make a vector that starts here and ends here. That's going to be my first vector. And I can make a second vector that starts here, ends here. And I set them to be perpendicular, meaning that the vectors multiplied by each other going to be set to be equal to 0. That's the perpendicular condition in mathematics. That's it. That's the big picture behind. And now how it goes in details goes like this. So I have first point O, which I'm defining using this equation that I know, only equation that I know. And I come first here, and then using vector u bar, which in this scenario shown in the picture will be equal to 0. This one will be equal to 0, but let's keep it on 0 this time. And then point P, which will be respect to this box-like body. I'm going to go this point here. I'm going to set this will be 0 as well. I'm going to create it like this. Start it here, end it here. And then the H will be in a one body only, so I can define it as it is shown. And now when I simplify it, I can express it as it is shown here. Final thing needed is this perpendicular condition. H transpose multiplied by KAB needs to be set to be equal to 0. That means that these two vectors will have 90 degrees angle with respect to each other. That's what it means mathematically. Let's do it. It will look very bad, but let's just make it happen. So this is my H. This is my K. And when I multiply them together, it's going to look like, well, I'm simplifying these components. And when I do the math, this is how it looks. That's my second constraint equation. Okay? Not easy, but doable. Okay? You agree? Are you still alive? Because I can see what I can see is like this. Okay, yeah, this was just an example. All right? So let's look at the one more example. Okay, here is a mechanism that, let me see, I have 15 minutes time. Maybe I can do a bit more than this, but this is a mechanism that I would like to create constraint equations. Okay, 2 moving bodies, 2 revolute joint, 1 primitive joint. Okay, here comes a big surprise. What is the number of degrees of freedom? Okay, hold on. I need to look at first this. Just a second. Okay, so let me take myself. Actually, I realize that I have less than 15 minutes left because we only have a 10 minutes break. Okay, constraint equations. Hold on. Oh, you don't see this. Just a second. Would you like to see the success rate of the constraint equation in class quiz? Yes. Okay, me too. Okay, so I need to do this, duplicate, and you will see this momentarily. Here it goes. Okay, what is that the constraint equation is doing for you? Okay, what that for sure is not going to do for you. Correct. Rotation of particle is for sure is not going to do that for you because nothing going to do that for you. There's nothing in this planet that can do for you. Okay, that's out. How much we have discussed about the dimension of the bodies? No discussion. Mass is related to inertial forces. Forces we have not discussed. So it's connecting generalized coordinates. But how is the success rate? Oh, so there is a voting which is it like 100%, 99%? Ooh, oh, oh, this has become to be too scary because when I see this red arrow to go like all the way to right, I'm like, oh my God, it's gonna happen. So you guys make me dancing. But no, thanks God. And the bad news is this: still we have one percentage that thinks that Earth is flat and the particle do have a rotational degrees of freedom. I don't know. I don't find this funny. I don't find it funny. Okay, the next one. Number of degrees of freedom. Would you like to see the mechanism again? Okay, you see it. It's here. I'm not going to switch this to presentation mode yet because I would like to go back to this in-class quiz. You have seen this before. You have. Can I go to constraint equations? I know that this is a maybe too risky business, but I'm going to show this slide to you. Think about this. Maybe this was too much. Maybe this is too much. Okay, okay. So, okay, now there is somebody saying that for sure it wasn't me. It wasn't me voting this rotational particle, but there was somebody. It was somebody. Okay, now they're saying dancing again. I don't know. Okay, let me take myself back here. Okay, what is the number of degrees of freedom? Can I take a look? How many we got? I did not check like how many answers we collect. 80, and now it's 68. So maybe there is still somebody thinking this. The number is increasing. So 70 students, 70, 71. Okay, please enter your answer. Cast your vote. No, this is not voting because voting would be a matter of opinion. This is not the matter of opinion. This is a physics based. And we got the 53 online participants, which I think it is okay number. It's okay number. Yeah, that's a good news. Okay, 76, 76. So can I close this? You guys all done? In in four, in two. Okay, now I'm gonna make you very scared, and you're gonna answer this incorrectly, and I will be saved. Okay, in can we go? We can go. All right. So here it goes. Okay. So if this is gonna be 100%, I need some time to process it. I cannot do anything here today, so I need some time because it may be this time 100%. Okay, let's just jump it and let's see. Oh, oh. Okay, this is becomes to be too scary business now. And now I need to make it a bit more difficult because it will happen this way. It will happen. Oh, it was close, but thanks God, we got votes saying that there is a 3 degrees of freedom. There are three Generalized coordinates Burr moving bodies, but not the correct solution here. 0 is also incorrect. Okay, let me take myself back here, and I will let you go soon, but not right now. Okay, I need to disconnect this one. Oh, you don't see it yet. Okay, here it goes. All right, so this is my example here. So I need to create constraint equations. Okay, so I'm going to use an equation, the only equation that I know, and I'm going to define this point O, P, and Q. All right, now comes the first temptation. You know, sometimes there is a temptation, and you need to be just not look at those temptations. What is a temptation here? Temptation is that you go from this reference coordinate system directly to point O. Not allowed. You need to go first here, the body reference coordinate system, and then back with help of vector U bar. So you need to put this temptation aside and do it using the only equation we know. Be consistent. All right. I haven't really looked at this TV series Temptation Island, but I guess that this is the same kind of story. I guess so. Not sure about that. But anyway, so it goes this way. We go to this point O by first traveling here and then back. So first here, which is vector R, we're taking the body orientation into account, and with help of vector U bar, we go back. This point has to be with respect to body reference coordinate system on its origin. So that's why these two components will be equal to 0, because it cannot move with respect to reference coordinate system, and reference coordinate system is located here. Makes sense? Okay? That's once you do the math, that's going to be your first two constraint equations. No surprising here, you multiply this one, multiply this by this, set that to be equal to 0. This one, multiply this by this, set that to be equal to 0. That's it. Second constraint is point P. It is common in a body A and body B. We know already how to do that, so there's no surprises here. So we first go into this point B by using this body A, and we do the same. We redo the whole job, but this time using the body B. And we set them to be equal. All right? So no surprises here, no surprises here. Vector U bar, we need to move positive direction, which is amount of L divided by 2. And once we do that for the second body, we go first here, then we take body orientation into account, and then the U bar. This time we need to move the minus direction. That's why minus L divided by 2. Because we here look in this direction. That's why minus L divided by 2. You set them to be equal, and that's going to be your third and fourth constraint equations. And the last one is going to be a primitive joint, where the motion of this point cannot move along the global y coordinate axis. All right? So I'm going to set this point, and I'm going to say that this row here have to be equal. Let's put it, this row here have to be equal to 0. So it's up ry, then this row multiplied by this vector needs to be set to 0. And that's going to be your fifth constraint equations. We did not have a time to look at the Jacobian matrix or kinematic analysis, but we'll do that next week. And kinematic analysis is an analysis where we can solve the motion using constraint equations only, nothing else. Just constraint equations. Okay, so what do you think? Is it going to happen this class that we're going to score 100%? Probably not. What do you think? Can do attitude, so it will happen because of your attitude. Very good. Okay, take it easy. See you guys on. Oh, I got 2 likes. So one is from Mustafa. I got 2 likes, 2 thumbs up. Okay, so yeah, they're guessing that there's not going to be dancing. It's all about up to you. So I do whatever you are telling me to do. Okay, but let's close this and see you guys on Monday then. Not yet, but I will do it that soon. Okay.